preparing solutions. So at the beginning of your notes here, there's a previous knowledge check. So take a look at this question, maybe pause the video and try it on your own and then double check your answer. So to complete this, we need to know what mass of lead 2 nitrate must be used to produce 350 mils of solution with a concentration of 0.125 moles per liter. Lead 2 nitrate has the formula PbNO32, and we are looking for a volume of 350 mils and a concentration of 0.125 moles per liter. We are trying to solve for the mass. So what we're going to do first is we're going to use our concentration formula and solve for N. So N is 0.125 moles per liter times 0.350 liters. Remember, volume has to be in liters here. Multiplying that out, we get number of moles is 0.04375. With our moles, we can then use our formula little m over big M. So we're going to solve in this case for little m. Little m is equal to moles times molar mass. So we need to find the molar mass of lead 2 nitrate. Remember, when we're looking at something with a polyatomic, we need the mass of lead, just one lead, so that's 207.2. There are 2 nitrogens, so 2 times 14.01, and there are 6 oxygens, oxygen, and we'll multiply it by 6. So 207.2 plus 28.02 and 16 times 6, I get a molar mass of 331.22 grams per mole. So we'll multiply our calculated moles, 0.04375 moles times the molar mass we just calculated. Sorry, it's a little bit hard to read there. And we get a mass of 14.490875 grams. I just copied all of the numbers from our calculator. Last thing we need to do is look at significant digits. So there are 3 significant digits in 350, and there are 3 significant digits in our concentration. Remember, leading zeros do not count. So we need to round to 3 significant digits, and we'll keep the 1, 4, 4. We need to round that actually up. So 14.5 grams is what we would need to dissolve. So a standard solution is a solution with a precisely known concentration. The term standard refers to a set value considered to be accurate and from which all others will be compared or based on. Basically, this is a solution where we really accurately know the concentration or the number of moles of something dissolved. It is the given concentration value in question, or if it was a lab and I had made the solution, I would give you the concentration value as well. The standard solution must be mixed with extreme accuracy. Most chemicals come in either a solid or a concentrated form, so we need to make solutions from a solid or a concentrated form. Note that we are not going to make solutions from gases. So when we are preparing a solution from a solid, we need to calculate the amount or the mass of solute required to form the desired concentration, and then mix that amount carefully with water following the steps below. So calculate the mass of, I just said, solute required. We're going to weigh the mass of the required solute in a weigh boat. And what that looks like is literally just like a little tray. It's plastic that we can scoop our solid onto on the scale. All right, so just keeps it contained, it's small, and we can rinse it out really nicely. We're going to transfer the solid from the weigh boat into a clean, dry beaker. Oopsie, that's really small. Clean, dry beaker. Needs to be dry because we don't want to add anything else into it at this point. Using a distilled water bottle. We just want to make sure that what we are dissolving is pure. We are adding no contaminants. We're going to dissolve the solid in the distilled water using approximately half of the final volume. So if I am making a 100 milliliter solution, I'm going to dissolve my solute in about 50 milliliters of water. We're going to transfer the solution to a clean volumetric flask. It does not need to be dry. And we're going to rinse the beaker and our stir rod and whatever else into the flask. So that's why we didn't use the exact 100 milliliters to our volumetric flask, which looks kind of circular like this, if you will. And it has just one line. It's a calibration line. So this only measures one volume. So in this case, it would measure 100 mils. So when I put my beaker in, it fills it to about 50. About half. Then I rinsed everything and I added maybe another 10 or 20 mils. So we just needed to make sure that we dissolved it in less than our full volume of 100 milliliters up here to make sure we had room to rinse everybody into. We're going to add distilled water until the bottom of the meniscus is on the calibration line. So the calibration line is like up in the neck of the volumetric flask. When we add water, it always makes a meniscus. And so when we talk about a meniscus, we're talking about the bottom of it. So it should look like this, where the meniscus is right on the calibration line. Okay? If the meniscus is low like this, we've underfilled. If it is above by a ways, we have overfilled. Then we're going to stopper it. So basically cap it. Okay. And invert, turn it upside down and right side up again several times to mix completely. All right. So we've prepared a solution from a solid. We also need to prepare a solution from a solution because, again, lots of things that we get, like acids, for instance, come in a very concentrated form, and we want to use a less concentrated form in our lab. So dilution is the process of reducing the concentration of a solution by adding more solvent to an existing solution. During the process of dilution, the volume increases while the concentration decreases. The example of this is making juice from concentrate. So like a frozen juice or lemonade. You get a very concentrated can of juice. And when we add it into our pitcher, we have to add the can of our lemonade, and then maybe, I don't know, I think 3 cans of water to dilute it. Okay, so it tastes good. Our volume has increased, and this was very concentrated. Once we dissolve our lemonade concentrate here, the concentration is reduced to something that we would actually maybe want to drink. So the dilution equation is C1V1 equals C2V2. It comes from our C is equal to N over V formula. If I rearrange and I multiply V to both sides, I get that N is equal to C times V. Now note that the number of moles of juice concentrate over here is still the same as the number of moles of juice concentrate within my pitcher. So N hasn't changed, but my concentration and volume have. So that's where the C1V1 is equal to the same number of moles, but a new concentration and a new volume. So we've combined these two, taken out the middleman of N, and gotten our formula here. All right, so the quantity of solute, or whatever it is we're using in this case, is not changing. So number of moles did not change. N1 is equal to N2. So let's use this. What volume of concentrated hydrochloric acid is required to prepare 1 liter of solution with a final concentration of 6 moles per liter? So C1V1, C2V2. We just need to make sure, like we were in gases, that we're using the initial conditions over here and final concentration conditions over here. So initial and final. So what volume of concentrated hydrochloric acid, what we are starting with, 11.6 moles per liter, is required to prepare our final solution with a volume of 1 liter and a final concentration of 6 moles per liter. So we're looking for V1 here. How much of this concentrated hydrochloric acid do we need to use? C1V1 equals C2V2 is our equation. Solving for V1, I'm going to divide both sides by C1 to start. So V1 is equal to, all we have to make sure is that our concentration units are the same, or if we were solving for a concentration, that our volume units are the same. Because we have moles per liter on both sides, we are good to go. All right, so C2 is 6 moles per liter times V2, which was 1 liter, divided by 11.6 moles per liter. So 6 divided by 11.6, I get a volume of 0.5172. And that unit would be liters from this guy here. We need to think about significant digits. There's 2 significant digits here, 2 here, and 3 here. So our final answer should have 2. Remember, leading zeros do not count. So V1 is equal to 0.52 liters. We need to use 0.52 liters of our 11.6 moles per liter to get a final concentration of 6 moles per liter in 1. All right, how do we prepare these? Well, very similar, but instead of weighing a mass, we now need to measure a volume. So we're going to use a volumetric flask again, so this thing that measures only 1 volume, but we're also going to use what's called a volumetric pipette. So these are definitely not proportional drawings. The volumetric pipette is not super giant, but liquid goes in that end. And we kind of use a suction bulb at the top to draw the air out of our pipette. So it sucks the air out, and if I've immersed this in a solution, this draws solution up. Okay, so like our volumetric flask, a volumetric pipette only measures 1 volume. So it has a calibration line as well. And we are looking to pipette or bring solution up, so that our meniscus sits right on that calibration line again. Oftentimes these are small volumes. So 10 mils, we can have a 5 mil, a 2 mil, 1 mil. I mean, you can get specific, but they're usually a whole milliliter. So a decimal point is not what we want to use. We try to, it's not, we can't measure 10.6 milliliters. We can only measure 10. You can get a 25 and a 50 as well. All right, so we said some chemicals are bought as a concentrated or stock solution and must be diluted. With stock solution, you must calculate the amount of water required for the dilution and mix the amount of solution, required for the dilution, and mix that amount carefully. So we have decided that we're using a specific volume of solution. We're going to use our volumetric pipette to measure that instead of a mass on a scale. So we are going to calculate the volume of stock solution required, and then we're going to add distilled water to our volumetric flask until it's half full. Then we're going to measure the required volume of standard solution using our volumetric pipette. So we're going to suck up our solution into the pipette until the meniscus is sitting right on the calibration line. And then we use our thumb across the top, kind of like transporting a liquid in a straw, to move this liquid into our volumetric flask. We transfer, like I just said, the stock solution to the volumetric flask. And then we add distilled water until the bottom of the meniscus is on the calibration line. So I've added whatever I've used my volumetric pipette to measure. Again, I have made sure that I've got water in here to begin with so that whatever I'm adding is diluted immediately. And last but not least, same step, we are going to stopper and invert several times to mix. Okay, so we've added water to the calibration line. We add a stopper. We add a stopper into the top here. Oops. And invert to mix it up. So on tests and quizzes, you would have to describe the procedure. It's really tricky because we actually haven't done the procedure, which is helpful to remember it. Make sure you take a look at the 2 videos below. A friend of mine who is a chemistry teacher in Calgary made those 2 videos, and I think that they're really great explanations on how to make a solution from a solid and by dilution. So you can actually see the process instead of just me describing it. When diluting, so adding a volume using our volumetric pipette to our liquid, when diluting all concentrated reagents, especially acids, we always add the stock solution or our concentrated solution to the water, not the other way around. The reason is if when I add an acid and water together, it is exothermic. Okay, so it gets really warm. If I'm adding an acid to lots of water, so I've got my pipette here and I'm adding drops of acid in, they'll quickly dissolve, but the concentration is low, so a low concentration of acid. Because I've added such a small amount of acid to water, it releases a little bit of heat. However, if I've got it the other way around, I've got my acid and I'm adding water to it, when I add a little bit of water, yes, it is a small amount, I guess, in comparison. However, my acid is very concentrated still, very concentrated acid. We haven't diluted it very much by adding a few drops of water. So when these mix, it releases a lot of heat because it's still so concentrated. And as I keep adding water, it keeps releasing lots and lots of heat. Whereas over here, we're diluting it so quickly that the amount of heat given off is so minute. All right, so we add an acid to water every time. And this is why we just are always in the habit of half filling our volumetric flask when I'm gonna pipette into it or transfer anything into it, because we just wanna make sure that we're always diluting something very quickly rather than the other way around, which is not what we want. It releases so much heat that it could break this kind of glass. There's some practice in your textbook here. I encourage you to take a look at it. I think this is actually outdated. This was from the other textbook. Double check online what questions you would want to do from the Nelson textbook. This one's from an older one.